By the end of this video, you will be able to contrast felsic and mafic lava composition, and you will be able to define viscosity and give examples of liquids of contrasting viscosities.
All right, so today we are here to talk about what comes out of a volcano. We know that there are different things that come out of a volcano. They can be solid, liquid, or gas. Today we just want to focus on the liquid stuff that comes out of a volcano, which starts underground as magma, and on the surface it goes from magma, it changes its name to lava. And we know that, well, I can't bring in lava. Yeah, that's kind of hard.
A little dangerous.
Yeah, a little dangerous, just a little dangerous. But I have the next best thing. I have lava that's crystallized and cooled, and now we have rocks that came from lava, and we have these, which we call felsic in composition, and we can see that they're typically light colored like this white, gray, tan, pinkish color. What's giving it the distinctive light color, Andrew? What makes it that light color?
Well, I mean, based on the name, feldspar and silica would make up a felsic.
That's right. Felsic is named for the fact that it contains feldspar and silica. That's why we call it felsic. So this is the other kind of lava that's typically dark in color, usually black. This is mafic, but it doesn't have the cool word association like felsic does with feldspar and silica. Do you know what minerals are typically in mafic rocks?
Well, the darker classic minerals, pyroxene, amphibole, and hornblende.
That's right, yeah, typically those minerals, which make it very iron and magnesium rich, which is actually where the word mafic is derived from, but so it's not really as interesting as felsic and easy to remember, but dark color, typically mafic, light colored, felsic. And so another physical property that makes these very distinct is not just their minerals, but the density of these. And if I could put these on a balance and find their mass and determine their density using volume using water displacement, I'd find that the mafic rock is denser than the felsic rock, and that's actually very important when it comes to tectonic plates and whether something's going to subduct underneath another plate, depending on what minerals or rocks that plate is actually made of. But when we're talking about lava, the liquid material that comes out of a volcano, we're interested in something that's going to definitely have a control on how eruptive our volcano is and how that lava typically flows, and also what type of volcano we typically see based on the different types of lava. So we're going to do a little demonstration here. I'm going to give Andrew some molasses, okay, and I have some water, and we are going to pour them down the little stream table, empty tray, at the same time, and we want to look at what happens with the water and the molasses when they're poured on just at a rather gentle slope, and kind of see make some observations about what's happening here. So we're going to do it on the count of three.
Okay.
So 1, 2, and 3. Oh, there's the water. And there is the molasses.
They're still going.
Still going. All right. That's a lot of molasses to be using. I could be using that for making some gingerbread, but we're going to use it to demonstrate a particular property of liquids, especially volcanic liquids or lava. So what do we observe about the water versus the molasses, Andrew?
The water and the molasses have different tendencies to flow.
Yeah, which one made it all the way down really quick?
The water.
Yeah, the water went really fast, and finally the molasses is catching up. So that's actually a very important property, that resistance to flow that the molasses seems to have. And we actually call that resistance to flow, that kind of stickiness or thickness that a liquid may have, we call that viscosity. And molasses is much more viscous than water. Water is like milk and soft drinks, iced tea, that would just flow very easily. The molasses is a liquid that is much more resistant. It took its time to get down to the bottom. you can probably think of other things that are in somebody's pantry, like is another viscous liquid you might find in somebody's pantry?
I mean, peanut butter would be one.
Peanut butter, yeah, sure. And speaking of peanut butter, we want to repeat this with peanut butter with another thing that you might have in your kitchen, and that's ketchup. So we're going to compare the viscosities of ketchup and peanut butter. We're just going to clean this up first. So we're going to repeat this little demonstration, except that now we're going to use ketchup and peanut butter, some of the things that we mentioned before. And the reason we're using ketchup and peanut butter is because when we talk about mafic and felsic lavas, ketchup and peanut butter actually are very, very close, like really close to the actual viscosities of mafic and felsic lava. And so the ketchup will be the mafic, the dark black, denser lava. And so that will be our ketchup because that's really the viscosity of mafic lava. So I'll give you the honors. And peanut butter is also a liquid, and it's also going to be our felsic representative. And felsic, as we said, contains a lot of feldspar and silica, which is why felsic is a really cool word. And we're just going to try and dump this out in our pan here and see what happens to the peanut butter and see what happens to the ketchup, which one is more viscous. Since peanut butter is to represent the felsic, we probably have a good idea of what we're going to be observing. So we're just going to do this. So you can pour your ketchup, and I'm going to scoop this out into the tray. I think that's good. So we've been waiting a couple minutes, and what did we observe?
The ketchup moved, but just barely.
Yeah, the ketchup moved a little bit. It's definitely a different shape than when you first poured it in. It's gone down a couple centimeters.
And the peanut butter hasn't moved at
Yeah,
all.
the peanut butter hasn't moved. So peanut butter is very viscous. Even though it's on a slope, we'd probably have to apply a significant amount of heat to get that melted a little bit and to actually get it to flow. And the ketchup, would, if it were heated up, would also flow much more easily, which tells us something about lava itself. That the temperature is also a big variable with lavas in how fast these are going to flow, whether we're on a relatively flat surface or we're on a sloping surface, which would be more typical on a volcano with steep or even rather gentle sides. All right, so we're back a few minutes later, and it's moved a few more centimeters. Yeah, so just because it's mafic, it doesn't mean it's going to flow like water. I know that if you've been watching the Kilauea volcanic eruption, some of that lava looks like it's moving quite fast, but it is much hotter than our room temperature ketchup. But it's just to get us an idea and a mental model, conceptual model of the viscosity differences between something that would represent mafic lava, which is our ketchup, and something that represents our felsic lava, which is the very, very viscous peanut butter, which really hasn't moved at all. But that doesn't mean mafic lava can't have a very important impact, and we'll see that in the next segment.
When you have finished watching the video, you'll be taking a short questionnaire that will ask you to rate your confidence on a scale from 0 to 10 in performing all of the learning objectives, where 0 is not confident or sure you can do any of the objectives, 5 is fairly confident or sure you can do some of the objectives, and 10 is very confident or sure you can do all of the objectives.